Hello everyone, my name is Jacek. I am going to give you a presentation on the influence of advanced finite element method on accuracy of results based on the case study of Big Silo. Let me start with a few words about my job. After that, I will discuss the case study comparing simple models and advanced models of Big Silo. So I live in Poland and I work in GT project. It is a consulting company with wide scope of services. We provide field investigations and laboratory soil tests. We elaborate geotechnical documentations and building designs. Recently, we also carry out ground construction works. Thanks to wide company profile, we have perfect workflow. Our team consists of experts in geology and civil engineering. I am structural engineer and I specialize in geotechnical designing. I will show you a few examples of my calculations. I often analyze deep excavations with slurry walls. Analytical methods reduce this problem to plane strain conditions. But thanks to finite element method, I can calculate it as a 3D model, as a 3D analysis. Moreover, huge advantage of FEM is that I can analyze influence of excavation on existing neighbors. On this picture, you can see deep foundation of power plant. More precisely, it is turbine hole. Not only the geometry was complicated, because of intensive dewatering by drainage wells, we had to assess a risk of internal erosion. So fully coupled analysis was necessary. From the left, you can see flow paths. Next is degree of saturation and velocity of filtration. This high-rise building was founded on jet grouting columns. During construction, the geodetic measurements were being compared with calculations. We had very good convergence between calculations and monitoring, so it made us sure that prediction of final settlement is okay. Otherwise, in case of differences between monitoring and calculations, we would be able to diagnose the problem at early construction stage and earn some time to figure out mitigation strategy. And believe me, this approach gives engineers a lot of comfort. Next example is couple of abutments. This was the subject of expertise. During construction, excessive deformations had been observed. So we were asked to analyze whether the abutments would be able to serve under full load or not. So from time to time, we analyze bridge foundations. Very often we design road embankments and railway embankments using finite element methods. Nowadays, rigid inclusions are more and more popular technique of ground improvement. On this slide, you can see two small tanks on soft soil, reinforced with displacement columns. There is a transfer platform between slab foundation and columns. It was a consolidation type of analysis. So I can present you the animation with dissipation of excess pore water pressure. Over time, objects to design become more and more demanding. This silo is an example of large-scale model, and it is also the case I'm going to focus on in this presentation. So some information about it. The silo was erected in 2013. It has 50 meters of diameter, is 70 meter high, capacity is 80,000 tons, 80, not 18. Organic layer had to be improved with 1,000 piles. This green layer here is a stiff sand layer. Below it, there is relatively softer clay layer. So as you can see, it is complicated problem of huge loads put onto compressible subsoil. At this moment, let me pose a question. If we really need heavy models, or how much can we simplify our models? I hope that the case of this silo will help us together to draw some common conclusions, but let's start from the beginning. In 2012, for the purpose of building design, I built a model. Let's call it a primary model. In the following chapter, I will briefly present primary results in comparison with settlement monitoring. First of all, let me present analytical solution of the problem. I don't know if you are familiar with theoretical background, so I will explain it briefly. Piles and soil among piles are assumed as one solid, so the calculations start from the level of pile space. When calculating settlements, we need to divide the space below foundation on sublayers. Then we calculate geostatic stress. And using this diagram, we calculate vertical stress change. This general diagram shows stress change distribution below circular loading. After that, we calculate settlement for each sublayer, and we continue calculations unless stress change is smaller than 30% of geostatic pressure. This 30% criterion is taken from old standard, which was in force in 2012. Nowadays, Eurocode says about 20% criterion. It means that in new standards, deeper contribution is taken into account. After summing last column, I got final result. So analytical method gives 14 centimeters of settlement in the center of silo. The depth of influence is more or less 40 meters. On this slide, you can see model of subsoil and pile raft foundation. This is primary model. As you can see, it is 3D model, but with some simplifications. First of all, I wasn't familiar with hardening soil model that time, so I applied standard mold coulomb. As one knows, this material model doesn't consider hardening effect. So in order to avoid overestimation of settlements, I had to increase stiffness parameters manually, according to the law of stress level dependency. Soil par interaction was modeled with contact elements. It was simplified model of interaction, linear function with cutoff after reaching bearing capacity of pile. Non-superstructure was modeled, so its rigidity was neglected. Of course, self-weight of superstructure was input as equivalent dead load. Primary calculations gave 13 centimeters of maximum settlement and large differential settlements. So as you can see, primary results correspond to analytical solution. Long-term monitoring gave us a lot of knowledge how the silo had been settling. This black line in the diagram is a trend line. After 7 years, it gets flattened, so we can assume that settlement process is finished. Geodetic measurements gave 16 centimeters of maximum settlement, so primary calculations on one hand underestimated maximum settlement, and on other hand overestimated differential settlement. Please note that 1/4 of the silo settles the most. It is because uneven soil layers. Taking benefit of settlement monitoring, I have built a new model considering my current skills and state of knowledge in order to verify the calculation approach I use and to verify procedures we apply to determine parameters. My first new model was not enough to match up to real settlements, so I was adding successive features just to get satisfactory results. You will see the details in a moment. Now it's clear for me that primary model was too shallow, so new model is deeper. New model exactly reflects ground conditions and geometry of substructure. On the right, you can see drawings from building design. The main improvement in new model is application of hardening soil material model. And it must be underlined that this is not a back analysis. There was no manipulation on soil parameters. Further, mesh quality was improved comparing to primary model. Exact pile soil interaction was applied. Based on analytical methods, we are able to predict real behavior of a pile and then implement it into software as functions. And also ground level is modeled. So rigidity of superstructure is partially taken into account. Again, please note that in this area, clay layer elevates higher, so this side is more compressible. This is why the part of silo settles more. And if I didn't know real settlement, it would be my final result. This analysis has been done with my standard procedures I currently use, and it was supposed to give satisfactory results, but it didn't. Black ISO lines represent monitoring. calculated 18 centimeters of maximum settlement. It's not a big difference in comparison with real 15-16 centimeters, but divergence lies rather in distribution of differential settlements. This model gives maximum settlement in center of silo, unlike geodetic monitoring. Next step of improving the model was application of small strain behavior. As you can see, calculated settlement was reduced evenly by more or less 1 centimeter, but still with the same incorrect distribution. My next step was modeling of full superstructure with shell and dome, as you can see here on this schematic cross section. Settlement distribution gets better shape. The silo tends to tilt on one side, but still it's not good representation of a real situation. As next step of developing my model, I added finite elements of storage material. And you can see it on this schematic cross-section. These are continuum elements with self-weight of storage material. Only top cone of storage material was modeled as load function. And this step gives the best improvement. We can see that calculated distribution of settlements is close to real one. It may be not a perfect match, but in my opinion, satisfying enough. And final step was application of geometric nonlinearity option. It means that additional effects from large displacements are taken into consideration in analysis. According to second order theory, I was expecting that this feature would intensify or would enhance the effect of differential settlement, but change in results was a quite a surprise for me, because there is almost no change in results. So these are final results of my multimodal analysis. Please note how many features are necessary to carry out advanced finite element analysis. Now let me demonstrate the results on advanced model. You will look on vertical stress change, a depth of influence zone, and moduli of subgrade reaction. Here you have some data about my model and my computer. Please note that the number of degrees of freedom is 700,000. It shows how large this model is. And thanks to fast hardware and high quality of finite elements mesh, total time of calculations is half an hour. That's really fast. So, okay, let me switch to GTS NX. This is a 3D model with complete structure and storage material. I implemented interface elements between storage material and the shell in order to model low friction between these materials. As you can see, mesh is structured. Finite elements are regular shaped. It helps to go through calculations easily. No divergence, no numerical instabilities during calculations. After calculations, results must be checked in order to detect any disturbances. First of all, let's see horizontal displacements. 6 centimeters at top, quite large, and vertical displacements. Now let's look at cross-section of the model. I will create a cutting diagram. Okay. Now we clearly see how settlements vanish along with the depth of the model. And let's check stresses. This is geostatic vertical stress in initial stage. and this is total stress. This is total stress including load from silo. Now I would like to see stress change generated by the silo. We need to do simple operation on results. Geostatic pressure must be subtracted from final stress, so we select vertical stress from final stage, and we also select vertical stress from initial stage. Okay. Maybe for better visibility, I will do some trick. Okay. Okay. These lines, black lines, are piles. So one can observe that the load is transferred to soil through piles. The largest stress change is under pile space. Now we will use ISO surface option to present stress change in more convenient way. This ISO surface helps us understand how stress change propagates and dissipates in a subsoil. And we can observe this famous bulb-shaped surface of stress change. As you can see, post-processing is a large advantage of GTS NX. Now let's analyze the depth of influence zone. We need to generate relation between initial geostatic pressure and stress change. We press calculation again. Then we select stress change. And we select vertical stress from final stage. Maybe for better visibility, I will adjust the legend. Okay. Okay, and this is the relation between stress change and initial geostatic pressure. When describing analytical solution, I mentioned about 30% threshold, which was assumed in old standards. Let's find it. Okay. Current codes assume that influence zone reaches 20% threshold. And some literature says even about 10%. Okay. So depending on different standards, we can calculate relevant depths of influence zone. For 30% threshold, it is more or less 40 meters. For 20% threshold, it is 47 meters. And for 10% threshold, it is 58 meters. Let's see corresponding settlement at threshold levels. They are something like 7 centimeters, 4 centimeters, and 2 centimeters respectively. In my opinion, in this case, the case of large silo, standard criteria are not applicable because we cannot neglect such values. So very deep model is required, at least 70-80%. Sorry, 70-80 meters deep model is required. And finally, let's talk about subgrade reaction moduli. Let me show piles. Okay. I will show you forces in piles. This is a diagram of axial force in piles. So subgrade reaction moduli is a long name. I prefer to call it springs. So let me call it simply springs. When calculating a structure, in structural software, engineers use springs to model soil foundation interaction. And for most of us, it's a magic. Hardly one knows how to estimate spring values. Usually engineers use some rough guidelines or experience. Finite elements method is a perfect tool for such calculations. I will show you how I calculate pile springs. So here we have axial forces in piles. For central piles, it is more or less 700 kilonewtons. We need to divide pile reaction by displacement. Again, we use a calculation option. And at this moment, I need to make one comment. Stress and displacements are two different types of results, which cannot be combined in this option. So I needed to add auxiliary construction stage to convert element results to no-load results. So I converted axial force in piles to pile reaction. I select pile reaction and I select displacement. Dividing reaction by displacement, we get the spring value. I also activate some auxiliary elements for better visibility. Okay. And this is the plot of pile springs. Let's check the values. 700 kilonewtons over 15 centimeters gives such a spring value, 4.5 thousandths of kilonewtons over meter. And this is the same in my model. Generation of springs under slab is more complicated. I will show you just final results. Okay, so maybe I will start from presenting stresses under the slab. So final stress just below the slab is more or less 50 kilopascals. The total load, I mean dead load and lift load generated by silo is 500 kilopascals. So it means that soil takes directly 10% of total load. After dividing 50 kilopascals over 15 centimeters, we get such a spring value, slightly more than 300 kilopascals over meter. And in my analysis, it's exactly the same value. For better visibility, I can check the auto range option. We can see lower values of spring in the center and higher at the edge of slab foundation. So I hope that you enjoyed this short workshop with GTS and Next. Now let's go back to presentation. We have just seen advanced model. Advanced finite element analysis may be very complicated and time-consuming. Let's see if there is any way to make it easier. I've prepared simplified model just to compare these two approaches. I will tell a few words about assumptions of simplified model. It is axisymmetrical model with average levels of layers. Main simplification regards soil material. I used more Coulomb model. One knows that this model doesn't consider hardening effects, so to avoid overestimation of settlements, I manually modified stiffness parameters applying this formula. This is a formula of stress level dependency law. Piles are modeled as embedded beams. It means that there is rigid connection between piles and soil. Simplified model contains only ground level of silo. The rest of superstructure is taken into account in a form of equivalent dead load. Results of simplified model are clearly larger than in advanced model. Maximum settlement is larger by 6 centimeters. Settlement diagram is almost linear. It is visible that displacement in lower part of model is overestimated. Let's see what happens when I replace more Coulomb model by hardening soil model. Results are very similar to those from advanced 3D model. The diagram of settlement is more realistic, is nonlinear, and it rapidly decreases below the influence zone. So changing simple more Coulomb to advanced hardening small strain model is the right step. So here we have very simple geometry and advanced model of soil material. And if you need to simplify your analysis, then think rather about this direction. Now we are able to draw some common conclusions. Firstly, about geometry. We can simplify geometry to a certain extent, but not too much. You should choose simple model type, but of course relevant to your case. If you analyze 2D problem, then do not complicate it with 3D analysis. And if you are not fluent in finite element method, you should better choose some specific cross-section and analyze it as a plane strain state. Nevertheless, dimensions of models should be large enough to cover influence. And extremely important thing is high quality of mesh. Finite elements should be regular and preferably rectangular. In presented case, we saw how important material model is. So simple models such as more Coulomb are applicable only in simple analysis. You should tend to use hardening soil model. If you don't know some parameters directly, then you may use some correlations or guidelines from literature. And finally, about analysis, specify construction stages. Do not skip any of them. Choose the simplest possible analysis type. For most cases, the stress type analysis is sufficient. So good luck with your models. Now, if you have any questions, I can try to answer. You can also write to me via email. Thank you for your attention so far.